Okay, today is lecture 18. Some of you got your tests back today. Those of you that didn't get them back, you'll get them back tomorrow. There is a solution sheet inside. And for the benefit of those that take this class on cable TV and DVD later, we'll do all the transaction as far as getting your tests back to you in the mail. So, and I will include a solution sheet along with your test in the mail. Actually, walking over here today, I thought of something that might kind of help put together some facts that were in Chapter 2, Section 9. They have to do with the first and second derivative, and I know this yesterday was our first encounter with kind of second derivative stuff. So let me see if I can help connect some things together and if we can get a visual of what they mean when you put them together. So let's say that we know at a certain point, I'll just call it A, that the derivative is 0. So think of what that means. Don't say it out loud yet. And we also know at that same A value that the second derivative is negative. First derivative is 0. Just that fact alone means what is happening at that instant?
Flat.
It's flat. So we've got a flat place. So let's say here is A. So wherever the corresponding Y value is, let's say it's there. So we know at that instant that it's kind of flat, perfectly flat. Probably nearly flat as it comes into there, and nearly flat as it leaves there. But at that instant, it's flat. All right? So that's what that means. Hopefully, everybody's coming up with that same response. What does this mean? Concave down. Is that consensus? Concave down? So if the curve is concave down, and at that instant it's flat, tell me what we have. A relative max. Does that make sense? These two facts together. Come up with the fact that if it's concave down, it's got to look something like this, right? And if it has that shape, then we're talking about a relative max. And in like fashion, if we have a place, another graph now, a new graph, where the first derivative is 0, and the second derivative at that location is positive, those two facts come together and say we're dealing with what? Relative min. So let's put them together graphically. At A, we have a flat place somewhere in the plane. That's this. And if the second derivative is positive, that means it's concave up. And if it's concave up, it's got to have this kind of shape. And if it has that kind of shape, we're dealing with a relative min. So those two facts together mean relative max. These two facts together mean relative min. So second derivative negative means concave down. All right, let's forge ahead into Chapter 3. The first section of Chapter 3. I don't think we'll complete this today. I'd be very surprised if we do. But we have that additional day, and this is kind of the last section we're supposed to do business with this week, so I think we're going to be okay time-wise. So we will get some so-called shortcuts today. We have the definition. In fact, we have two definitions. Primarily, I think we've been using this one. And the algebra and the whole process gets a little cumbersome after a while, so we're all ready, myself included. We're all ready for some of the shortcuts. So there's probably the primary definition of derivative that we use. and if you'll remember, definition of derivative was on the test. It's an important concept. We're kind of moving beyond it now. Not that it's, not important anymore. We're just going to get quicker methods of getting there. Also on the test, you probably remember at least part of this, f of x minus f of a all over x minus a. This is kind of the alternate definition of derivative. And if we take a limit as x approaches a, that accomplishes the same thing. Probably with a little subtle correction here, we would then get the derivative at a, as opposed to the derivative at x. But the process gets us there to the derivative. So we use that one more often than not, and in validating some of the shortcuts, we're going to still go back to the derivative, but then once we get beyond it and we see what it is all the time, then we can use the shortcut. So what have we seen to this point in time? We have seen that the derivative of a constant with respect to x is 0. That's come up. In other words, it didn't appear at all in the derived version. We have seen that the derivative of x with respect to x was 1, and in fact it kind of looks like 1, right? dx over dx kind of has that appearance of 1. We have seen in an example the derivative of x squared with respect to x. Anybody remember what that was? That was 2x. So the slope of the tangent on that curve at any point is twice the x value, whatever that happens to be. I think we've also seen the derivative of x cubed in an example, which was 3x squared. Now, that's probably enough to build a pattern, but that doesn't necessarily, just because it appears to be a pattern, doesn't mean that it's going to work all the time. If we use that pattern, and I'd like to validate that pattern one more time, in terms of a specific number. We haven't done this one yet. But if the pattern that appears to be working to this point continues to work, what would the derivative of x to the fourth be? 4x cubed. So tell me what that pattern that you have picked up, what is it with x to the fourth?
Bring the power down.
Okay. Good. Bring the power down, so the integer power 4 would be now a coefficient, and then we'd take x to 1 degree less. Okay, so most of you said that, and you came up with 4x to the third. So that's still doubtful. I mean, you're trusting what you've learned before or the pattern that you're picking up. But let's see if, in fact, that is true, and then see if it's true all the time. Then we can kind of use that pattern from today forward without having to go back to this definition all the time. So if our function is x to the fourth, a little bit of computation, but I think it can go fairly quickly, we want to find what the derivative is. So by definition, limit as h approaches 0, the function at x plus h minus the function at x all over h as h approaches 0. Does that look right? Familiar? Ready to move on from that? I think we all are ready to move on, but let's tolerate it a couple more times. X plus h to the fourth. First term is what?
X to the fourth.
And I also have another ulterior motive here in expanding x plus h to the fourth, is we can validate kind of a pattern that you maybe haven't thought of it in that way before. And then when we get x plus h to the n, and we don't know what n is, we can express everything in terms of n. So x to the fourth, second term would be 4. How do you know it's 4? Okay, Pascal's triangle will work. We'll come up with another reason why it's 4. X cubed, because the x's are descending, right? And the h's are ascending. Next term, 6x squared h squared. 4x h cubed. h to the fourth. From that, we'll subtract x to the fourth. Okay. Let me, before this gets cluttered, and that's going to happen if we kind of continue with the same process. If you'll take, for the coefficient, kind of the next coefficient, if you'll take the exponent, which in this case is 4, times the coefficient out in front, which is 1, right? There's a 1 here. 1, 4, 6, 4, 1. So this 4 times the 1, and divide it by the number of this term, which this is the first term, that ought to generate the next coefficient. Does it? 4 times 1 over 1, there's the next coefficient. Let's see if that pattern works. 3 times the 4 that's already there, divided by 2, because this is the second term. 12 divided by 2 is 6, which is the next coefficient. See if it works all the way down the line. 2 times the 6 that's already there, divided by 3, because this is the third term. Does that get us the next coefficient? Okay, it does. Let's keep going. 1 times the 4 that's already there, divided by 4, because this is the fourth term, ought to generate the next coefficient. Have you seen that particular pattern before? Okay, but we can write it down when we don't know what the number is. We know it's n. We can write that down in terms of n, which that becomes a little helpful when we try to do this in the general sense. So we will replicate that pattern again. All right, x to the fourth minus itself. Everything else should have an h. As long as h is not 0, we can reduce those. And then if we let h approach values that are very, very, very close to 0 on what is left, every term that has h in it should disappear. Is that correct? So the only term that doesn't have h in it is that one. So this disappears. This disappears, and this disappears. So is that the answer that we thought we were going to get based on the pattern that we had going? 4x cubed. I think that's what we thought we were going to get. That still doesn't prove that it works all the time. So let's validate that this, in fact, does work all the time. Then we can use that shortcut from this point forward. So let's say our function is x to the n. So it gets a little bit more cumbersome here because we don't know what n is. And let's say that n is some nice positive integer, so we can kind of use that same pattern. So we want the derivative. So by definition, it should be x plus h to the n minus x to the n all over h as h approaches 0. This is going to be a little messy, but we'll clean it up. The next step is messy, and then we'll clean it up in the step that follows. X plus h to the n. Let's expand that. What's the first term of that expansion? X to the n. And you could write out all those factors. You're going to take x times x times x times x times x. How many times? N times, because there are n factors. So that's got to be the first term. Now let's generate the coefficients the way we did before. Let's take n times 1, divide it by 1, and that'll get us the next coefficient, which is n. Wasn't that true? When you cube something, the second coefficient is 3. When you square it, the second coefficient is 2. we just raised something to the fourth. What was the next coefficient? It was 4, right? 1, 4, 6, 4, 1. So it was 4. So when we're raising it to the n, the coefficient is n. And if you know the shortcut, you know that that certainly comes into play, because that's the exponent. X ought to be to the n minus 1 degree less, because they're descending as we go. That also comes into play, right, in the shortcut. And then we ought to have an h to the first. Is that all right with everybody? All right, next coefficient. Let's take the exponent times the coefficient that's already there. Divide it by 2, and that'll be the next coefficient. We don't know what n is, so we just have to write that whole mess down. So there's the coefficient, whatever that happens to be, and there's a pattern here that's nice and clean as we go. Especially if you've never used this pattern, you might want to use it at some point with x plus h to the 11th. I don't know that you want to go down Pascal's triangle all the way to the 11th line. So here's a way of getting there term by term. X should be to the what? 1 degree less, which would be n minus 2, and h should be squared. This is going to be kind of an ugly step here, but we'll clean it up in the next one. All right, now we're going to do the same thing. We're going to take this exponent times this coefficient. So that becomes n times n minus 1 times n minus 2. There's already a 2, but now we're going to divide this whole thing by 3 because we're at the third term trying to move to the fourth term. So how do I divide it by 3? I just put a 3 in the denominator. I'm going to clean that up by putting a 1 there. That doesn't change anything, does it? And I'm going to clean this one up by putting a 1 there. And I'm going to clean this one up by putting a 1 there. Doesn't matter, right? Divide by 1. That's legal. X to what power? And h to the third. All right, now we've got a little pattern thing going on. Without doing the exponent times the lead coefficient divided by the number of the term, tell me what the next coefficient is going to be based on this pattern that you see going. All over 1 times 2 times 3 times 4, so 4 factorial, right? We'd have x to the what here?
N
minus 4 and h to the fourth. So there's a pattern that's going on. I don't know that we need to continue.
We don't.
In fact, what's going to happen, I mean, I'll just put a little dot, 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 and then the last term eventually is going to be what? H to the n, right? So there is the f of x plus h. We took x plus h to the n. We got this whole mess. From that, we'll subtract x to the n. All of that gets divided by h, right? I told you this step would be kind of ugly. I think it lived up to the prediction. So let's try to smooth that out just a tad. And I'm not going to write any more terms beyond this. Why would I write more terms beyond this? What are we going to eventually do? We're going to drop out x to the n with x to the n, right? What's the next thing we do?
Bring out the h.
Factor out an h. Well, when I factor out an h out of this term, there isn't any more h. When I factor out an h here, doesn't it leave an h? And doesn't it leave an h in every other term after that? So with those terms that still have an h in them, what's going to happen to them? They're going to disappear. So I'm going to basically stop with this term and then put my dots in there. And then we know that every term that still has an h is eventually going to disappear. So we're going to have, by definition still, x to the n plus n, x to the n minus 1 h. n minus 1 all over 1 times 2 n minus 2 h squared plus dot, dot, dot. And then the last term is going to be h to the n. So x to the n minus itself, they're going to drop out. We're going to factor out an h. So when we factor out an h out of this term, then we just have the n and the x to the n minus 1. Every other term, when we factor out an h, will have an h left in it. So that has an h, and every term after that has an h. Is that correct? As long as h is not 0, we can reduce those. And then we have a bunch of terms that still have h left in them and one term that doesn't. So the one term that doesn't have h in it is this term. So that remains. Every other term that has h in it, which is every term that follows, right? Every term that follows has at least h. Some have h squared, h cubed, h to the fourth, whatever, higher degrees of h. They all drop out because h is approaching 0. So we're left with this, n times x to the n minus 1. Is that the pattern that you thought was going to be the case for some binomial, or in this case just x, raised to the n power? So if you haven't used that or seen that before, frame that, put a star by it, because that will be an important shortcut. And we'll all be thankful that we don't have to use that long-winded f of x plus h stuff every time from now on. It saves a lot of work. So if the function is x to the n, then its derivative is that same n times x to 1 degree less. Is that all right? Now, you're not going to have to do this proof that we just did. That's not a test question. I don't think it's out of bounds as far as looking at it in class, but that's not a test question. But using this shortcut, certainly you'll have lots of opportunities to do that. Now, we don't see like x to the 4th by itself all the time. We don't see x to the 7th by itself all the time. If we did, that'd be easy based on what we just decided. The derivative, which is still everything we've called it to this point, slope of the tangent, instantaneous rate of change, it's still all those things. We just now have a quicker way of getting there. What's the derivative of x to the 7th? 7 x to the 6th. That is a shortcut. Do you believe me that that's a shortcut? You see what would be involved if we had to use the definition. We would raise x plus h to the 7th, right? I don't want to do it either. I mean, I can see that look in your eyes. I do not want to do that. So let's all kind of be thankful that we have this nice, clean shortcut. Right now, we have an idea that this works for positive integers. X cubed, x to the 4th, x to the 7th, x to the 11th, x to the 21st. It actually works a lot in a lot more cases than that. Suppose that we have, for our function, let's suppose it's not just x to the 4th. Let's suppose it's 5x to the 4th or 11x to the 4th. Well, we'll see that more often. So we have a constant times the function. So the derivative says, I mean, just think about what a derivative is. It's a limit. Wouldn't the two pieces of the limit both have c in them? Could we factor that c out in front? That c could be factored out in front. So basically, lead coefficients in this process kind of come along for the ride. Okay? they're there in the first case, they're going to be there in the derivative. We just factor them out in front is all we do. So this allows us to, if we have 11 x to the fifth, we can bring the 11 along for the ride. It kind of gets factored out in front. And then we take the derivative of the variable portion. What's the derivative of x to the fifth? 5x to the fourth. So our end result is 55x to the fourth. So that goes with any lead coefficient. Back on our shortcuts, we said the derivative of x cubed, and we had validated this in other problems. We said it was going to be 3x squared. That is true now, right, by our shortcut. We said the derivative of x squared from other problems we've already done was 2x. That works, right? Shortcut works. Exponent times the same thing, x to the 2 minus 1, which is that. We said that was 1. Does that still work? Mm-hmm. That'd be 1 times x to the 0, which is 1. So that works. Now, if we just have a constant by itself,
0.
does this pattern actually still work?
0.
Now, I don't think that that's the best way to think about this. The derivative of a constant, you know what a constant looks like. A constant is a horizontal line. If you think about tangent lines, well, you really can't be tangent to this without coinciding with it. And what's the slope of every line that coincides with this one? 0, right? They all have 0 slope. So the derivative of a constant certainly sounds like it ought to be 0. But does the shortcut also work? C is the same thing as cx to the 0, right? And we would take the exponent times the stuff that's already there. Well, the exponent is 0. Does it really matter what else follows? 0 times whatever else follows is going to be 0. So the shortcut really does get you 0 in this case. But probably easier to think of it in terms of a horizontal line. The slope of every horizontal line is, in fact, 0. I think we've done this. I think we've done that actually within the last couple days. We multiplied by the conjugate of the numerator, then we let h approach 0. If you'll check back, I think we got 1 over 2 square root of x, which is really 1/2 x to the negative 1/2, isn't it? So does that shortcut work for this as well?
Yep.
Yeah, it does. So x, the square root of x, is really x to the 1/2. So if the power rule, exponent rule, works, then we ought to be able to take the power, right, 1/2 times x to 1 degree less. 1/2 minus 1 is negative 1/2, which is that, right? So it's going to work for rational exponents as well. Will it work for negative exponents? It will work for negative exponents. So if we have a function, let's say it's 4x to the negative 6th. The 4 is a coefficient, so it comes along for the ride. The derivative of x to the negative 6th, according to this power rule, is what?
Negative 6 x to the negative 7.
X to the negative 7th. Okay, a common mistake is to make that negative 5, but that's not 1 degree less. That'd be 1 degree greater, right? So negative 6 minus 1 is negative 7. It kind of depends on what you're going to use the derivative for. Usually it's common to go ahead and multiply the monomial stuff, the numerical stuff, and then depending on how you want to use it, just put x where it belongs. In this case, x to the negative 7th belongs in the denominator.
Why are you doing with the constant in 2 steps? Like, I just learned you would just multiply negative 6 by 4.
Right.
And then you would just go straight
You
to
eventually end up doing that. Well,
negative-
I'm trying to separate
right.
just kind of bring the coefficient
Right.
along. You don't really change that or mess with it. What you do pay attention to is the variable piece.
Right.
But ultimately,
So you can just
right,
go
you're going to
straight
multiply
to
them
that
anyway. Right.
if you want.
You're going to take 4 times the negative 6, right? So that's fine.
Okay.
So you don't have to separate it like I'm separating it here. All right, little quick exercise at your seats. What is that?
X to the negative.
Don't say it out loud. Okay, Chandler, what do you got?
Negative 1 over x squared.
How many of you got that? That seemed to follow the pattern? 1 over x is x to the negative first, right? Same thing. So it ought to be negative 1, x to 1 degree less, which is that, right? Negative 1 over x squared. Now, do you know something about a curve just by the nature of its derivative? Well, I think we do here. Here's an example. That's an easy curve to plot points on, and but you may have a good mental picture of what that looks like. If you didn't, I still think we could get a pretty good general idea about that curve from its derivative. Is it negative 1? This is kind of a stupid comment, not unlike many others in here. Isn't negative 1 always negative? Right? And isn't x squared always positive, except where x is 0, and that's not used anyway, right? So always negative over always positive, what is this derivative? It's always negative, right? So if the derivative is always negative, what is the entire curve doing? It's decreasing. So is that helpful in graphing? I think it sometimes is very helpful in graphing. This has a vertical asymptote at x equals 0, so this is an asymptote. At x equals 0, this also has a horizontal asymptote. If you took a limit of this function as x approaches 0, you'd also get 0. So this is a horizontal asymptote. And without plotting a single point, if the curve is decreasing, which it has to be, because the derivative is always negative. Well, it's only got 2 things it can do. It can either do this or this, right? To use both of these as asymptotes. And if it's decreasing, doesn't it have to be down here? Isn't that decreasing? And then it takes a little intermission at x equals 0, doesn't exist at all. And over here, it's either got to be up here or down here. Which one? It's got to be the top one, because it's got to be doing what? It's got to be decreasing. So without plotting a single point on this function, we have a pretty accurate picture of what it's doing, just based on 2 asymptotes, vertical asymptote, horizontal asymptote, and the fact that the derivative is always negative. Nicole?
But if you take the second derivative, won't it become positive?
Yeah, now the second derivative, which on this one, we can tell, I think, what's going to happen to the second derivative. This piece of the curve is described that, concave up or concave down. That's concave down. So we would expect the second derivative here to be negative. And this piece of the curve is concave up, so we would expect the second derivative to be positive. So there will be a change in the sign of the second derivative. In fact, we have a way of finding that now. If this is the first derivative, what's the second derivative? 2x to the negative third. Is that correct? Which is 2 over x cubed. Isn't that negative when x itself is negative? Isn't that over here? Concave down? Isn't this positive when x itself is positive? So that justifies what we have going on over here. Very conveniently, the derivative of a sum is the sum of the derivatives. That would really make things confusing if that were not the case. So we've got this y value that's defined in terms of some f of x, and it's got some other piece to it, call it the g of x. If they're added or subtracted, we can add or subtract their derivatives. Now, I'm not going to write this all out, but if you think all the way back to the definition, it'd be the limit of this big sum anyway. And don't we take limits of sums by finding the sum of the limits, right? So we would just take them individually and evaluate the limits anyway. So the sum or difference of the derivative of a sum or difference is the sum or difference of the derivatives. So that gives us the ammunition to do something that looks like this. This would be a hideous, ridiculous problem by the definition of derivative. But it's not bad. Even though we've got some ugly-looking terms, it's not bad with this shortcut that we have today called the power rule or the exponent rule. Now, we have sums and differences, so we can take each one individually, find its derivative, and add them or subtract them, whatever is the case. Derivative of x to the fifth. Derivative of 17x cubed. Okay, 17 times 3x squared, which is 51x squared. Might want to take this one a little more slowly, because this term is really, what, 1/3 x to the 1/3, right? Cube root is x to the 1/3. What's the derivative of 1/3 x to the 1/3? 1/9 to the negative 2/3, right? Subtracting 1 from the exponent. You might want to rewrite this one, or at least think about it as that. 5 over x squared is, well, it's being subtracted. Negative 5x to the negative second. What's that derivative?
X to the negative third.
Plus 10
X to the negative third.
x to the negative third, right? So none of these are that bad. And really, the last one's the easiest of all, right? Derivative of a constant is 0. So any issues with getting any of these terms as the derivative of the predecessor? Now, this might be an issue with somebody. This is plus, even though this was minus. Do you see why it's plus? Because the negative 2 times the negative 5 that's already there. Product of two negatives came back with a positive.
Would you want us to rewrite the last two terms?
It kind of depends on what you're going to do with them. If we had a specific number in there, for example, if we were doing the f prime of, I'm thinking of something that has, let's say, 8. It might be helpful. I don't want to raise 8 to the 4th, but I'm looking out here. It might be helpful in this term if we had this term written as 1 over 9 x to the 2/3. Or it might be more helpful to somebody else. That would be the cube root of x, and then we could square that result, right? Would be one way of accomplishing that. So it kind of depends on what you're most comfortable with, because if we were putting in 8, I'd want to be able to take the cube root of 8, which is 2, and square it, which is 4, and that becomes 1 over what?
1 over 36.
36. right? Or the other number.
So for you, we can just leave it as x raised to the 2 squared.
When we don't really know what we're going to do with it, I think it's fine to just leave it like this.
Okay.
If we're plugging in a number and it might be helpful to us to rewrite that, then fine. Now, you might get directions in WebAssign that say write it without any negative exponents. Then you could write it in this form. Write this one as 10 over x cubed. So just be prepared to put it in some form that you might ask to have it put in that form, but I'm okay with these when we don't really know what we're going to do with it. Okay, last problem today. That's the one you're all looking for, right? The last one? Let's say, I was going to use that smart board today. I guess I have to build up my courage a little more before I do. Let's say we have this. It's a polynomial, cubic polynomial. Find the point or points, possibly, where the tangent lines are horizontal. Here's kind of where we're headed on this problem. Is if we were going to make a sketch of this cubic polynomial, wouldn't it be nice to know that there's a point here and the tangent line's horizontal, and there's a point here and the tangent line is horizontal? We'd probably be able to connect those dots pretty nicely. This is pretty common for a cubic polynomial. To increase into here, leave here fairly flat, enter here fairly flat, leave here fairly flat. Is that pretty typical for a cubic? Kind of have that S-curve shape. So if we could find the places where the tangent lines are horizontal, we're well on our way to getting a good sketch of this thing. I mean, some other points that would be important would be the intercepts. But excluding the intercepts, these are probably the two most important points on this curve, where it potentially changes direction. So we want to know where the tangent lines are horizontal. Take that question and give me something else that you know what to do here, Jonathan.
Can you find the derivative and set it equal to 0?
Does that work?
Yeah.
Okay. Find the derivative and set it equal to 0. Isn't that what we want to happen? We want to know where the slope of the tangent is 0, horizontal, right? 0 slope. Slope of the tangent is 0. What is the slope of the tangent? It's the first derivative. So, and now we have a shortcut, so this process should be a little bit faster. What is the derivative of the given f of x?
Negative 12x minus 6x squared.
Okay, minus 6x squared. Sounds like we've got consensus on that. There's the derivative. We set it equal to 0.
You can pull out
Negative 6x.
Pull out a negative 6x. In the first term, it's in there, what, twice? Is that right?
Yes.
And then here, plus x.
Yeah.
Is that correct?
0 and...
Now, if you ever want to check something, just redistribute it real quickly. It doesn't take but a couple seconds. This times this ought to be back here, which it is. This times this ought to be back here, which it is. And the nice thing about it being factored, we can set each factor equal to 0. X equals 0. Or x equals negative 2. Now, let's go back to the direction. Find the point or points. Are we there yet?
No.
No, we're well on our way. We know at x equals 0 something, and at x equals negative 2 something, the slopes of the tangent lines are 0. So where do we find those somethings?
Plug it in.
Plug it into the original.
Good, to the original. That's important. If we plugged it into the derivative, what would we get? We'd get 0. That's how we found them. We just found them by setting the derivative equal to 0. So we don't want to go back in the derivative. Whenever you're plotting points, go back to the original x, y relationship. So we want the f of 0 to go there, and we want the f of -2 to go there. I'm going to move this sheet. Any questions before it gets moved? So the f of 0, 5 minus 6 times 0 squared minus 2 times 0 cubed is what? 5?
Yes.
Yep.
So that ought to be a point where the tangent line is horizontal. The other point was -2 something. So we need the f of -2. Anytime you're plotting points, go back to the original function. So what do we have here? 5. That'd be 4 minus 24. That'd be -8 times -2 plus 16. End result is -3. So I always like to check the question again. Find the points where the tangent lines are horizontal. I think we now have them, right? So if we were going to make a sketch, which we're not asked to do here, but we will be asked to do here pretty soon, we would find 0, 5. There's a little flat place there. And -2, -3. There's a little flat place there. Probably, now we'll be able to validate this pretty soon. Probably this graph does what? Decreases into here? And I'm using some terms here that, do you know how to validate that it decreases? How would we do that?
You would do a number line and to the left of the point.
Okay, all we care about is to the left of -2, what is it
You
doing?
could just plug in a value. and
Plug it
see if
into
it's
the
positive or negative. So
Derivative.
Derivative, right? We're going to use the derivative to validate, but this probably decreases. It leaves here fairly flat, enters here fairly flat. We know that for a fact because how do you know I have to connect that dot to that dot? It's continuous because it is a polynomial. All polynomials are continuous. So you basically, there's no doubt, how do you get from down here to up here? You've got to increase. The derivative would back that up, and then you would probably find out from the derivative that this thing heads off in this direction, right? Now that's rough. That's a sketch. But based on those 2 points, that's probably a fairly good idea of what this function does. Now we're not finished with 3.1, but we will finish it up tomorrow in class.